Hi, my name is Drew. I tutor a number of topics in mathematics, but today we have the following problem. We want to determine whether the following planes, which these equations that you see on the board here, are parallel, orthogonal, or coincidental. Now, coincidental meaning basically they're the same plane; they just lie on top of each other. Now, technically speaking, if two planes are coincidental, then they must also be parallel. But because, so these two things aren't mutually exclusive, but because we have separate options here, then it follows that we're probably going to assume that parallel means that they are parallel, but they're separated by some sort of distance of some kind, and they don't intersect anywhere. So with that in mind, a couple things that you could do. You could definitely go through long computations using vectors and a bunch of other things to try to figure out some of these answers. And one of the ways you could do it is definitely like a plug and chug kind of way. Try to find values of x, y, and z and see if you can solve this system. But what we want to do is we want to make your life as easy as possible. So we want to just start with the simplest thing that you can possibly do, right? So the first thing that we want to do is check orthogonality. That's the easiest computation that you can make. So let's go ahead and do that. In order to find, so by the way, the definition of two planes being orthogonal, or one of the ways that you can determine whether two planes are orthogonal, is if if the normal vectors to the planes themselves are orthogonal, right? And that basically, and we can determine that by the dot product. So if we take two normal vectors, do the dot product of these two normal vectors, and if they equal 0, then it tells us that these two normal vectors are orthogonal, which means that the planes themselves were orthogonal. Now, because these equations are in this form, we can find normal vectors to these planes fairly easily because they're just the coefficients of the variables that you see here. So the first one here, we're going to call this normal vector n, and that's just going to be the coefficients, which is 2, 3, and -1. And then we'll call this normal vector m, and that's going to be these coefficients 6, -5, and -3. So we're going to go ahead and do the dot product of these two vectors. That's very messy. And the dot product of two vectors is just a multiplication component-wise of the vectors, and then you just add the values together. So in this instance, we do the first components, multiply them together, we get 12. Second components, we multiply them together, we get -15, and then the last components, multiply them together, we get +3. 12 minus 15 is -3. Oh, goodness. -3 plus 3, which is clearly 0. So with this very quick and simple calculation, we have determined that the planes are indeed orthogonal because the dot product of the normal vectors is 0. So the answer definitely is orthogonal here. Now, suppose we had not gotten 0 in this instance. Well, now just because we find some solution to, because we could find for instance, a line solution to these equations, just because two planes intersect does not necessarily mean that they're coincidental, right? So we could find, for instance, that these two things are not parallel, but we could also find that they're also not coincidental, right? And ways that we could go about doing that would be basically solving this. One thing that we can notice, by the way, if we look at these equations, is the first term and the third term here. I could multiply the top by 3 to get 6x here and -3z here, in which case, if we were to subtract the two from each other, then we would get that these terms would cancel, and we would get something in terms of y. And in fact, we would get some sort of value for y. In this case, once you do all the work, you add these together, you would basically get like 14y equals 47, which means that y is equal to 47 over 14. And this here, this value of y, right, we can take to mean that for y equals 47 over 14, there's always going to be a solution. There's going to be some x and z that we can plug in that solves both equations, right, for this value of y. So that tells us that they do intersect at some point, right? And when we reduce this, then we could say, okay, well, is it true that all values of x and z solve these equations here, right? In other words, no matter what I put in for x, y, and z, they will always solve the equations. Now, I mean, in fact, you could probably just plug and chug that and to see if that's true. But these are just things that to notice when you're looking at these things and kind of thinking about them in some other way than just computing values. Anyway, so that's the end of this answer here. If you have any more questions, just give me a message and I'm happy to answer that. Good luck.